Okay. Hi. My computer seems to have recovered. Sorry about that. So I'm going to go ahead and pick up where I left off from part one and share this screen. Okay. So what I was talking about in part one was how silicon stacks up in regards to crystal structure and phase diagram and defects, similar concepts that we had talked about before. Um, but the big difference here is that while it is a silicon crystal, um, it's a much different crystal than we are used to talking about with um, structural materials. In that these crystals, instead of, a lot of times in structural materials, you want to have a very fine grain structure. You want to have lots of very small grains um, to impede the dislocation motion of dislocations and strengthen the material. With silicon and other semiconductor materials, the goal is exactly the opposite. Right? You want to have um, as few dislocations as possible. You want to have one single crystal, and you want to have no impurities that you don't put there on purpose. Right? So the goal here is a perfect, or as close to perfect as possible, silicon crystal. And since we are basically looking for the opposite result, right, we're going to need a much different method of creating these materials. And so the main method for making silicon single crystal material is called now I might butcher this pronunciation because I've never really heard anyone tell me the proper way, but I usually say Trikalski. Maybe that's wrong. If you know the proper pronunciation, you can set me straight. But this method, this Trikalski method, is a dominant one for growing silicon wafers. And it's shown here schematically on this first figure here at the top right. And so what you have is a crucible that is heated, usually an RF supply, right? So you're going to be moving the electrons around in this crucible, right? The friction of those electrons moving through the material, heated up a lot, that's going to eventually melt the silicon, right? Silicon melts at, I think, 13 or 1400 C. And so you take this crucible, you load in polycrystalline silicon that has been purified, right? So you want to start with as pure material as possible, right? So you've got pure silicon, right? 9999999, as pure as you can get it. You may also add in the dopant material that you want to be in your final crystal, whether you're growing right N-type, where you add a group 5, or P-type, where you add a group 3 element. And then you have an evacuated chamber, right? So you evacuate it and you backfill with argon, so you can have an inert atmosphere to control contamination. And then you heat the whole chamber up to above the melting temperature of silicon, so that you have a molten material. That provides the raw material for growing the crystal. Now, to grow the crystal in a controlled way, you start with a very small seed crystal, right? So this is, say, I don't know, half a centimeter in diameter. You want to pick a high-quality seed that's a single crystal, and then you're going to orient it in the holder with the desired crystal face pointing in the direction that you want. So you may want to grow single crystal silicon that has a particular plane perpendicular to the growth direction, right? So you may want to have the 111 direction facing up, or the 100 or something like that. So you're going to orient the seed properly, and then at the beginning of the crystal growth, you bring that seed in contact with the melt. And if we recall some of our earlier work with homogeneous versus heterogeneous nucleation, right? The surface energy is much reduced in a heterogeneous nucleation, right? So it is unfavorable, relatively unfavorable, under these conditions to nucleate a new grain, right, in the melt. Because, remember, homogeneous nucleation requires large degrees of undercooling, right, to create a baby crystal nucleation site that is above the R star value and will grow spontaneously. So the only available place, right, and also the crucible is kept above the melting temperature also. So the only available place for the crystal to grow, for these atoms in the melt to find a place where they can incorporate themselves into a crystal, is on the surface of this seed. And so they do on that surface, and then the seed is withdrawn, right, which provides a location for new silicon atoms to grow, to add to the growing crystal, right? And so you get a seed that becomes a very large boule as the material is drawn out of the melt. And growing a high quality crystal in a controlled way here is dependent upon managing the thermal gradient here at this solid liquid interface. Because what you want is you want the liquid to stay hot, right? And the heat needs to go up through here because you want that thermal gradient to exist across this boundary where the melt is hot and the solid is not, and that provides that maintains the heterogeneous nucleation at this interface. And so that means you have a thermal gradient that is acting to conduct heat through the crystal boule, and that is the main way that one of the main ways that heat is lost in this scenario, which it must be lost because remember the energy, the thermal energy of a molten material is much higher than a solid material, and as it makes that transition, right, that difference in energy is given up. That's the heat of fusion. So not only do I have a thermal gradient, but as I'm solidifying, I am releasing heat that then must be transferred through the material. And so there's a lot of heat that is being given up. And so to get a good high quality crystal, the seed is pulled out of the melt, right, at a very slow rate. And we have heat loss via, here I'll scroll down, via radiation, right? So this boule, even though it's not molten, is still really hot, right? Say 1000 C or greater. And so it's radiating to the walls of the chamber. I also have convective losses, right? So I have argon that's flowing in and out of this chamber that's carrying away some heat. And then I also have conduction that goes through the neck. But remember, the seed is very much more narrow than the growing crystal, and so there's not a lot of cross-section for that conduction to occur. And so we lose most of our heat via radiation, the lesser through conduction, and a small amount, lesser through convection, and a smaller amount conduction through the neck of the boule. So, and not every part of the crystal is the same quality, right? So we're going to incorporate more impurities on the outside of the material, and also in this necking material as we are changing the growth conditions, right? Once we reach a steady state growth, then we'll get a high quality crystal. And so you can grow very large boules with this Tsiolkovsky method, as shown here, right? This is probably a dated picture, so maybe even greater. The industry was for a long time driving towards bigger and bigger boules, because that means in later steps, as we'll talk about, making microfabrication of devices is a planar process, right? So when you do a step, you do it on the whole surface of the wafer, right? So if you have a bigger wafer, you can make more devices at the same time which means that your cost per device goes down. And also, as you are decreasing the size of an individual transistor and putting them more densely, right, you can pack more of them into a given size of boule, right? And also there's the cost, there's the economics factor in here. And you say, okay, well, to make a bigger boule, I need to make a bigger furnace, a bigger crystal growth chamber, basically retool all of my infrastructure, build a new factory basically around this size silicon wafer. And if you build a new factory, you want to keep it running all the time. So, eventually, if it hasn't happened already, right, the industry is going to reach a point where it's not economically feasible to make a bigger boule because you will be making so many devices out of a single boule that maybe it doesn't make any sense to keep your crystal growing furnace running all of the time, right? And so then you've got dead time, and that is another factor that increases. So there's an optimal size, yeah, okay. So Tchaikovsky works very well for silicon, and that's one of the reasons why it's so used so much. For compound semiconductors, right? For example, gallium arsenide, that's 3,5 material. Tchaikovsky is used in a different way, and it's given a different name, right? This is called the Bridgman method, and it's based on similar principles, where we have a seed crystal and a thermal gradient, but it's not drawn from a melt. Instead, it's solidified from polycrystalline material in a boat, a ceramic boat, right? So we have a two-zone furnace, we have a cold zone and a hot zone with a thermal gradient, and so as that thermal gradient, or as the furnace is moved through the heater, right? I can move this thermal gradient through the material, and if I have a seed crystal at one end, right, as the thermal gradient is moving, it will form a molten region, which will then re-solidify on that seed crystal, right? So it's very similar in concept to the Tchaikovsky method, except basically laid down on its side. And so you're going to, because I have a compound semiconductor, I need to be careful about my relative amounts of arsenic and gallium. And arsenic and gallium have different vapor pressures, right? Gallium is, I believe, much higher. And so solid arsenic is provided within the chamber to maintain an overpressure of arsenic to ensure that we have a good stoichiometry between gallium and arsenide in our resultant material. And like we saw before, the orientation of the seed crystal will dictate the orientation of the single crystal that is grown. This is going to produce, right, smaller size crystals that are commensurate with the lower usage rate of gallium arsenide material relative to silicon. Okay. So back to silicon. You can grow Tchaikovsky method, and that suffices for many applications. But if you need to have higher purity silicon than is possible with the Tchaikovsky method due to impurities from the crucible itself, right? So this crucible is made of something, right? Graphite or quartz, which provides the opportunity for oxygen, especially, to diffuse into the melt and then be incorporated into the crystal, right? If you want to have a higher purity than that, right, because the impurity is coming from the crucible, you need to get rid of the crucible. And so that is done using another method called float zone growth. And with this method, you start with a boule that looks similar to what you end up with in Tchaikovsky, except that it is not grown slowly, and so you get polycrystalline silicon within the rod. And that polycrystalline silicon is transformed into single crystalline silicon by melting and resolidifying one section of the rod at a time, right? So you have a boule here that is sitting on top of a narrow neck where the seed is, and instead of moving the crystal relative to the heater, we move the heater relative to the crystal, right? So the heater will start, say, down here and move its way up, and as it's doing so, it is creating a molten zone that then re-solidifies back on the seed, right? So I have no contact with the crucible. So if I start with very pure polysilicon, I end up with a very pure single crystal material. And I can get higher purities, say maybe 2 orders of magnitude better. And part of the reason why you get such a high purity is because of the tendency for impurities to segregate. The distribution across a solid-liquid interface of a particular impurity in silicon is not equal. This is called the segregation coefficient, K, and it's defined as the concentration in the silicon, or the solid, over the liquid, right? So as we see here, let's take this first example of arsenic. Arsenic is an N-type dopant, and it has a segregation coefficient of 0.3, meaning that 30% of the concentration in the liquid there's less concentration in the solid than in the liquid, right? So what that means is as you're solidifying the material, you're rejecting impurities, right? Most of these coefficients are much less than 0. As you're solidifying the material, you're rejecting the impurities into the melt. And so you can model this progressive increase in concentration as you melt the length of the rod with this expression here, and this will be used in one of your homework problems. But what it allows you to do is, in a way, to sweep the impurities from one end of the material to the other, right? Because they are constantly being rejected into the mold, right? I am going to have more of the impurities, right, in the molten region, and that pushes them to one end, right? So for this example, if I were to start melting here, and I'm tracking the concentration of an impurity, right, it is increasing because, as the liquid concentration increases, right, with the same coefficient, the solid concentration is going to increase also, but still be below where it was in the before we melted the material at all. And so this allows us, as we melt and re-solidify, we could even do it more than one time, we're moving the impurities to the end of the crystal, right? And so that allows us to just basically cut off that end of the crystal and remove a lot of those impurities all at once. And so, certain high quality detectors and laser applications may require very high quality silicon, which you can produce with this method. It's also going to be more expensive. And so you can dope using the float zone. You can either start with doped polysilicon, or you could have a region within your feed rod that has a doped pill, right? So you'd have, part of the polysilicon feed rod would be, a pill with a higher concentration of your impurities, or you could have gas in the chamber that diffuses in from the outside. But because of these distribution coefficients or these segregation coefficients, right, getting a consistent concentration is more difficult across the whole crystal. Okay, so this next crystal growth method is not covered in Campbell, but it is helpful for more exotic materials in some respects, and also for insulating similar crystals, and that is hydrothermal growth. So hydrothermal growth is different than Trikolsky in that you are not melting and re-solidifying the material. Instead, you are dissolving and redepositing the material. And in hydrothermal growth, instead of having a concentration dependent or a concentration and temperature dependent solubility um, in the crystal or in the molten material, right? Here we have it in another solvent. So in hydrothermal growth, you have a thermal gradient also, where in your reaction chamber, you would have seed crystals, feedstock, so that would be polycrystalline material, and then you have solvent that fills in the space around them, and you have a hot zone and a cool zone. And what hydrothermal growth relies on is the solubility in that solvent of that particular material that you're trying to recrystallize be a function of temperature. And so what happens is, let's say for instance, which is the more common case, that you would have an increase in solubility in that solvent at a higher temperature, right? So I would have my feedstock down here. It would be some polycrystalline material that I'm getting the atoms that I'm going to put in my single crystal. And so because this is hot, I have more solubility of this feedstock in that solvent. And because it's hot, I develop a convective flow within my chamber, right? Because generally hotter materials will expand, and that reduces their density, and so they're going to float up, cool down, become more dense, and then sink back down, right? So I get this convective loop. When they cool down up here near the seed crystals, right, their solubility for that feedstock decreases, right? So it wants to come out of solution, and the best place for it to go is to deposit on these seed crystals. So it deposits there, is incorporated into the growing crystal, and over time, right, as this process continues, I consume the feedstock and I grow these single crystals. And this allows you to grow many relatively large single crystals simultaneously. You're kind of just limited by the size of your autoclave, the size of your chamber. And this technique has been used here at Wright-Patt in the Sensors Directorate and in the Materials Directorate to grow uranium dioxide crystals, which are hard to grow by any other method. There also, hydrothermal growth is used to grow industrially single crystal quartz, right? So you can see here, this is maybe a dated picture of a very large autoclave growing very many crystals simultaneously. The figure on the left here is an example of solubility of germanium nitride in 3 molar ammonia. And here it actually shows, this is a bit of an anomaly, but a decrease in solubility as you increase temperature. And so that would change how you would set up your cold and hot zones, but you could still use hydrothermal growth for this type of material, even though the normal case is to have higher solubility as you go up in temperature. Okay, last little bit here, wafer prep. So going back to silicon grown by Cherkolsky method, once you build a big long boule, right, you need to prep it before you can build a device on it. So you're going to cut off the ends of the boules because the quality is not as high as you are either increasing the diameter or tapering it down because you're changing the growth rate. You also have a higher impurity and defect density in the outer diameters, so you're going to machine away some of that lower quality material, leaving you with basically a cylindrical boule. Then you're going to slice that into wafers and grind and polish those wafers to be a very flat surface. And then along the regions of the boule, probably before you slice it, they do X-ray diffraction to confirm the crystal orientation that they wanted to grow. And then once they've confirmed that, there's a system that microfabricators use to identify the crystal plane direction of a particular wafer, right? So here, for instance, this first example, I have 111 crystal plane parallel to the surface, and it's p-type material, right? And so that is signified by just one flat side on the wafer, right? For n-type, I would have, you know, a 45-degree angle, right, and so on and so forth, right? I'm going to grind the end of the wafer to make it to distinguish, you know, what the crystal direction is and what the dopant is of that particular wafer, because they're all the same to the, you know, visibly to the workers who are processing these. Let's see here, right? And so, yeah, so they're etched and polished, right? So you want to end up with a flat, high quality, doped, single crystal silicon substrate. And that becomes the substrate that we're going to base all the rest of the microfabrication on, and becomes the material that we are then going to process, right, forward from here to build the device.